Recently, I have been troubleshooting a radiated emission issue on a client's PCB, showing here, okay? And as part of the troubleshooting process, I need to measure the clock signal in time domain. As I was speaking to the clients, they said, oh, you know, the clock signal is almost like a sinusoidal waveform rather than a trapezoidal waveform. That's what they said, because they measured using their oscilloscope, in which I really doubt, right? So in this case, I measure the clock signal myself, and I'm making this video to show you that when it comes to measuring a high frequency, high speed signal, such as a 100 megahertz clock signal, the do's and don'ts, and things you need to take into account when you make such measurement. Okay. For the demonstration, we're using a 500 megahertz oscilloscope. Ideally, I would use a 1 gigahertz oscilloscope to measure a 100 megahertz clock signal. But if you get a gigahertz oscilloscope, you will find most of the time they will provide you with a passive probe set, and then the passive probe set will only work up to 500 megahertz. So if you want to better probes, you have to purchase a separate fed probe or active probe that works all the way up to a gigahertz or 1.5 gigahertz. Okay. If you look at the passive probes that often come with the oscilloscope, so for example, in this case, this is a 10-to-1 passive probe. It's a 10 mega ohm, 13 picofarad for 1 mega ohm, 6 to 24 picofarad inputs. Okay, so it says that in the label of the probe. What does this mean then? Well, really it means that the oscilloscope will have a 1 mega ohm input impedance, and this probe would have 9 mega ohm impedance. So when you connect the probe to the 1 mega ohm impedance, you form a 10-to-1 voltage divider. But because of the parasitics we mentioned, right, it's not really that you can build a pure resistance as 9 mega ohm or 1 mega ohm. You will inevitably have some parasitic capacitance in parallel with this resistive component. And as we will show you here, that when the frequency is high enough, that these capacitance become a low impedance path for the signal you measure. Therefore, they distort the signal you try to measure in a way that we call it, sometimes call it loading the circuits. And in this video, we're going to demonstrate that by using a 10-to-1 passive probe such as this, the measurement result is actually not really the true signal. And as a comparison, we also will be demonstrating this homemade resistive probe, right, that actually works all the way to gigahertz and has minimum loading compared with a passive probe such as this. Before we start measuring the 100 megahertz clock frequency, the first thing we need to do is check the probe. Okay, so this is a 500 megahertz oscilloscope. So in terms of bandwidth, it's not really sufficient for measuring 100 megahertz clock frequency, but we just use this as a demonstration. First thing I often do is I check whether the probe needs to be compensated or not. So this is, as you can see, I have a very short lead connected to the ground and measuring the reference signals here. As you can see, I sort of just compensated the signal, so whatever I measured is a pretty good signals here, right? So if I can zoom in, you can see I have good rise and fall time of this signal. Often, if I don't do a compensation check, what you get is sometimes there's a little bit light compensation, or sometimes people do overcompensation as this, right? So in either condition, you won't be able to measure the signal accurately. So in this case, I'm happy with the signals I'm measuring at the moment. Okay, so that's the first thing I did, which is compensates the probe. The second thing is, as I show here, this is really my ground lead, so it's kept as short as possible, so just enough length to place this ground on the ground pin of my chip, and I'm gonna measure the clock signal using the tip. Okay, so this is the PCB board, and this is the microcontroller, and this is the flash drive. Between the two, clock signal chip selection and some data lines. And what we're going to do is measure the clock frequency using a short lead probe, passive probe. So what I did was I measured using this probe tip between the ground pin and the clock pin, and I got the waveform and I saved it, right? Just to let you know. Okay, so now if we look at the waveform, you see this is really what we measured. As you can see, the frequency is about 99 megahertz. It had a peak to peak about 3.1 volts. But if you look at this signal, it's not bad, isn't it? It's not a sort of square wave as a clock frequency, a clock signal like we are more familiar with, but rather it is more like between a sinusoidal waveform and a trapezoidal waveform, right? But you know, this is the clock signal that I can measure by using a 10-to-1 passive probe. And you know, we did two things really to make the measurement as accurate as possible, which is shorten the ground lead and also compensate the probe. But here we go. This is the results we got by using a 10-to-1 passive probe. Now I'm going to switch to another probe and show you the results. Here I show you what is most likely the situation when my client was troubleshooting the boards, where they use this long lead grounding wire to measure the clock signal. As a result, you can see the signal is a lot more distorted. Here I show you another way of measuring a clock signal. This is a homemade resistive probe tip, okay? It has a 1:40 ratio and it works all the way up to 1 gigahertz. So very, very useful for high frequency, high speed measurement. I will dedicate perhaps a separate episode to introduce this probe, how it works, and how to construct one. Okay, but for the demonstration purpose of this video, you can see that this probe is connected to a coaxial cable, and if I show you, it is terminated with 50 ohm rather than 1 mega ohm in a scope. And as you can see here, the attenuation at the moment is 20 times. It should be 40 times, but unfortunately, this scope does not allow me to manually change into 40. So I have to either select 20 or 50. So in this case, I'm selecting 20, knowing that whatever the value I measured in terms of the amplitude, I just need to double it in my mind, okay? So as you can see, this is the clock signal that I measure using this probe. In my opinion, this is a much better waveform compared to the waveform that I measured using the standard 10-to-1 passive probe that the manufacturer provided. And also, as you can see here, that the peak-to-peak voltage I measure is about 1.45 volts, 1.45 volts. Now, if I double it, it will be like 2.95 to 3 volts. So in terms of the accuracy, this probe shows very good accuracy when you are using it to measure high-speed signals such as a clock signal. So this basically shows you the results. Okay, so hopefully you enjoy this video and I'll see you next time.